Hey everyone, I'm Shane Luke, and I lead AI and machine learning for Workday. Personally, I have been deeply interested in this field since I was an undergraduate, and that was at a time when AI was purely an academic pursuit. So working in this field as a career is unexpected for me and pretty special. And with so much attention on these technologies lately, I thought I'd take some time to talk to you about what AI and machine learning actually are, and how the recent advancements in the field impact enterprise software. Let me start by addressing a question I often hear. What is the difference between AI and machine learning? You often hear that machine learning is a subset of AI, but that isn't quite true. So let's start with a very basic definition of AI. Using computers to emulate tasks only humans could previously perform. There are many machine learning applications that don't fit this definition, like generating synthetic data, analyzing large-scale data sets, or performing complex system simulations. That said, almost all AI systems today do employ machine learning as a major component, which is why you hear that. So while AI and machine learning don't have such a simple superset to subset relationship, it is true that pretty much all of the things you hear referred to as AI do employ machine learning. That could be ChatGPT, autonomous driving, or image generation. However, AI systems are just that. They're systems and typically quite complex, employing not only multiple machine learning models, but also other parts like data extraction and training loops, content moderation policies, or real-time sensor systems like in autonomous vehicles. So, just like most vehicles have wheels, but not all vehicles have wheels, and wheels are employed on most vehicles, but also used elsewhere, AI and machine learning have a close but not entirely overlapping relationship. So what exactly is a machine learning model? And what does it even mean for a machine to learn? Machine learning models are composite mathematical functions that perform statistical inference. There's a lot there, so let's unpack it a little bit. Statistical inference means we are using the statistical properties of existing data to infer or predict what an output should be when faced with new data that historical data represents. The models themselves are generated by running the underlying mathematical functions that make up the composite. So for example, in the case of neural networks, you would have activation functions to set values for neurons. You would have a loss function to quantify the error of the model. You would use backpropagation to calculate the gradient of the loss function with respect to the current parameters of the network. And then finally, you would use gradient descent, and that's where you would learn a set of unknown parameters that can perform the statistical inference we talked about. So that last step is the learning in machine learning. We run gradient descent as an optimization algorithm to find a set of parameters that minimize the loss function. It's worth noting that for any non-trivial case, we cannot exhaustively search the space of possible parameters. That space is far too large. We seek to learn a set that is good enough for whatever task we are training the model to perform. So we set this threshold of what is good enough. And when we, as the programmers, are happy with the performance of the model with a set of these learned parameters, we can stop our training and use the model to perform inference on new data. Models will tend to drift over time and may suddenly perform poorly on new data, so they are retrained, sometimes very frequently, and that process is a continuous one and a very important part of real-world production machine learning systems. While there's been a lot of attention on machine learning-based AI systems lately, we have all been interacting with very sophisticated machine learning systems for years. Every social media interaction, every internet search, and most e-commerce interactions have machine learning systems serving content, modeling user preferences, and generating recommendations. Whether you choose to call those AI or not is somewhat subjective, but they are certainly complex machine learning-based systems and are widespread, have been for a long time. We are now seeing the power of this technology applied in enterprise settings, including, of course, here at Workday. We run thousands of models across thousands of tenants on a globally distributed platform. They power features in recommendations, document intelligence, anomaly detection, and natural language generation, just to name a few. While we see many great opportunities to employ these technologies, there are two important things to note. One, not everything in enterprise systems should rely on AI and machine learning. The second is that, at least for us here at Workday, the technology is intended to assist or augment people, not replace them or make unsupervised decisions. Much of the backbone of your core business processes just aren't a good fit for AI and machine learning. You don't want inference from a machine learning model driving your payroll, ensuring tax compliance, or setting HR policies for your organization. But for things like recommending skills or learning content or career opportunities, machine learning models are a great tool. Likewise, in financials, for things like large-scale anomaly detection, document processing, or forecasting during a planning process, machine learning models are a great tool, and all of these are deployed in our products here at Workday. So models are a great match when the following conditions are met. You don't need a deterministic system. Machine learning models are probabilistic systems. A deterministic system is one whose output is always the same given the same input. You also have to have sufficient representative data to learn your model's parameters. And lastly, there's no way to directly compute whatever output you are after. It's counterintuitive, but it's actually very easy to get to completely uncomputable problems. Worker skills is a great example. We have about 140,000 skills in our Skills Cloud ontology. If we assume an average worker might have 20 of those skills, the number of possible combinations is over 10 to the power of 84. That's more than 10,000 times the number of fundamental particles in the visible universe. Way too large to compute. So there are great opportunities for AI and machine learning to deliver tangible value in the enterprise. But doing so requires a different approach than in consumer, where data is typically aggregated across all users and has little or no regionalization requirements. In enterprise settings, frequently data cannot be aggregated, must stay in a particular region, and must adhere to strict security and access constraints. As a result, a machine learning-based AI system designed for the enterprise data must have components to deal with all of these constraints and to do so with high reliability. A great example comes from large language models, which are too large to run in a tenanted fashion. In other words, we cannot run an LLM for each tenant. But for us, it is not acceptable to aggregate sensitive customer data to train a large language model. So we have invested in approaches that allow us to train adapters using techniques like LoRA and its variants. LoRA stands for low rank adaptation, and it is a technique used to efficiently tune large models. In standard fine-tuning, all the learned parameters of the model are updated, making each tuning run similar in scope to base model training, and making it infeasible to dynamically load potentially hundreds of billions of weights at inference time. So a single model cannot efficiently serve many tenants. With LoRA, we decompose the update weight matrix into two low-rank weight matrices, which still capture enough updates to the base weights to achieve the goal of tuning to each tenant. The rank of a matrix has a somewhat technical definition, but for our purposes here, we can just focus on the fact this makes our update matrix much smaller. Using this technique, we reduce the size of our updated weights by several orders of magnitude, making tenanted training and runtime loading of these adapters feasible and without ever mixing sensitive customer data. Another good example is our global regionalization. We offer central development environments in both the EU and US, and inference is served from 5 different global regions. I love this field and could talk endlessly about AI, but I have to get back to actually building Workday AI. I hope you enjoyed the content today. From this talk, I hope you got a good sense of what AI and machine learning really are, how we think about applying them in an enterprise setting, and the major considerations that drive how we design our systems. Thank you for having me, and enjoy the rest of the series.